In 1950, physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory when the conversation turned to the possibility of extraterrestrial life. The group discussed recent UFO reports, the vastness of the Milky Way, and the statistical likelihood that intelligent civilizations existed somewhere among the 400 billion stars in our galaxy. And then Fermi asked a question that no one could answer. Where is everybody? It was not a joke. It was a paradox. Because if the universe is as old as we know it to be, 13.8 billion years, and if life emerges wherever conditions allow, then intelligent civilizations should be common. Some of them should be millions of years older than humanity. Some of them should have developed interstellar travel. Some of them should have colonized the galaxy by now, spreading from star to star, building structures visible across light years, filling the cosmos with signals, probes, and evidence of their existence. But we see nothing, we hear nothing. The galaxy is silent. And 74 years after Fermi asked his question, we still do not have an answer. Because the mathematics of cosmic life predict that we should be surrounded by civilizations, the silence predicts that we are alone, and both cannot be true. Which means either our understanding of life is fundamentally wrong, or something is preventing civilizations from making themselves known. Something we have not yet discovered, something that might already be affecting us. The Fermi Paradox is not a mystery because we lack data. We have mapped billions of galaxies. We have cataloged thousands of exoplanets. We have identified dozens of worlds and habitable zones where liquid water could exist on their surfaces. The Kepler Space Telescope alone discovered that roughly 20 to 50% of Sun-like stars host Earth-sized planets in regions where life as we know it could survive. The mystery is the absence of contact, as if even a tiny fraction of those planets developed life, and if even a smaller fraction of those evolved intelligence, and if even 1 in a million of those achieved technology capable of space travel, the galaxy should be teeming with evidence. We should see megastructures around distant stars, massive engineering projects that harvest stellar energy. We should detect artificial signals and radio frequencies, deliberate transmissions meant to announce a civilization's presence. We should find artifacts in our own solar system. Probes sent millions of years ago by explorers who passed through before humans even existed. But astronomer Frank Drake, who founded the search for extraterrestrial intelligence in 1960, spent decades listening to the cosmos with radio telescopes and heard nothing. The Breakthrough Listen project, funded with $100 million and equipped with the most sensitive instruments ever built, has scanned millions of stars across multiple frequencies and found no confirmed signals. The James Webb Space Telescope has analyzed the atmospheres of exoplanets searching for biosignatures, chemical imbalances that only living processes could create, and so far has detected no definitive evidence of life. The universe appears empty, and the longer we search, the more disturbing the silence becomes, because there are only a few possible explanations. Either intelligent life is extraordinarily rare, rarer than any statistical model predicts, or intelligent life destroys itself before it can spread beyond its home planet. Or intelligent civilizations exist but choose not to communicate, hiding deliberately in a cosmos that punishes those who make themselves visible, or they are communicating, and we are too primitive to recognize the signals. Each explanation is unsettling. None of them can be ruled out. The mathematical foundation of the Fermi Paradox was formalized in 1961, when astronomer Frank Drake developed an equation to estimate the number of detectable civilizations in the Milky Way. The Drake equation multiplies 7 variables: the rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, the probability that life emerges, the probability that life develops intelligence, the fraction of intelligent species that create detectable technology, and the length of time such civilizations remain detectable. When Drake first calculated the equation using conservative estimates, he predicted that there should be between 1,000 and 100 million detectable civilizations in the galaxy at any given time. Even the lowest estimates suggested that humanity should not be alone. But the equation relies on assumptions we cannot verify. We know the rate of star formation, we know that most stars have planets, we do not know the probability that life emerges from chemistry, we do not know how often intelligence evolves, and we certainly do not know how long technological civilizations survive. In 1966, astronomer Carl Sagan and physicist Iosif Shklovsky published a book analyzing the Drake equation and suggested that the real bottleneck might not be the emergence of life, but its survival. They calculated that if the average technological civilization lasted only 100 years before destroying itself through war, environmental collapse, or resource depletion, then at any given moment the galaxy might contain only a handful of active civilizations, separated by such vast distances that contact would be statistically impossible. This became known as the Great Filter Hypothesis. The idea that somewhere between the origin of life and the colonization of the galaxy, there exists a barrier so difficult to overcome that most civilizations fail. And the terrifying question is whether humanity has already passed the filter, or whether it still lies ahead. Because if the filter is behind us, if the hardest step was the emergence of multicellular life or the evolution of intelligence, then we are one of the few species in the galaxy to reach this level of development, and the future is open. But if the filter is ahead of us, if every civilization reaches our level of technology and then destroys itself within a few centuries, then we are not special. We are simply next. Astronomer Robin Hansen formalized this idea in 1996, analyzing the statistical distribution of observable life in the universe. He found that the absence of evidence for extraterrestrial civilizations suggests that at least one step in the evolutionary chain from non-life to galaxy-spanning civilization must be extraordinarily unlikely. Either life itself is rare, or intelligence is rare, or technological societies self-destruct before they can expand beyond their home worlds. The data does not tell us which step is the filter. It only tells us that the filter exists. And then, in 2018, astronomers at Pennsylvania State University published a study analyzing the potential for intelligent life to spread through the galaxy using a model. Based on percolation theory, the mathematics of how things diffuse through a medium, they found that even if interstellar travel is slow, even if civilizations expand at only a fraction of the speed of light, a single species could colonize the entire Milky Way in less than 50 million years, a blink of time compared to the galaxy's 10 billion year age, which means if any civilization had achieved interstellar travel at any point in the last 10 billion years, we should see evidence of it. The galaxy should be full. But it is not. Why has no one colonized the Milky Way in 10 billion years? Until now, this looked like a mathematical puzzle, philosophical question, an abstract debate about probabilities and assumptions that could not be tested without actually finding extraterrestrial life. But it was not abstract. Because in 2015, astronomer Tabitha Boyajian at Yale University was analyzing data from the Kepler Space Telescope when she noticed something that should not have been possible. A star, cataloged as KIC 8,462,852 and located 1,470 light-years from Earth, was dimming in a pattern unlike anything ever observed. Most stars dim periodically as planets pass in front of them, blocking a small fraction of their light. But KIC 8,462,852, later called Tabby star, dimmed by up to 22%, far more than any planet could cause. The dimming events were irregular, asymmetric, and non-repeating. Boyajian and her team analyzed every natural explanation. Comets, asteroid fields, protoplanetary disks, stellar pulsations, instrument errors, none of them fit the data. And then astronomer Jason Wright at Pennsylvania State University proposed a hypothesis that made international headlines. He suggested that the dimming could be caused by a megastructure, an artificial construction built by an advanced civilization to harvest energy from the star, partially blocking its light as seen from Earth. Wright was careful. He emphasized that this was the least likely explanation, that natural phenomena almost always account for astronomical anomalies. But he also acknowledged that if humanity was serious about searching for extraterrestrial intelligence, we needed to consider technological signatures, not just biological ones. And a Dyson swarm, a collection of solar panels or habitats orbiting a star to capture its energy, would produce exactly the kind of irregular dimming observed at Tabby's star. The Breakthrough Listen project immediately turned radio telescopes toward KIC 8,462,852, scanning for any artificial signals. They found nothing. Follow-up observations with ground-based telescopes continued for years, monitoring the star for additional dimming events. And in 2018, astronomer Tabetha Boyajian published a study showing that the dimming was wavelength dependent, meaning it was most likely caused by dust, not solid objects. A natural explanation, not a megastructure. The alien hypothesis collapsed, but the episode revealed something more disturbing than the discovery of an alien civilization. It revealed how unprepared we are to recognize one, because for 2 years, Tabby's star was the most studied object in astronomy. Dozens of telescopes, hundreds of scientists. And the only reason it became a global sensation was because it behaved in a way that seemed artificial. If the megastructure hypothesis had never been proposed, the star would have remained a footnote, an unexplained anomaly catalogued and forgotten. Which raises the question, how many other stars are behaving strangely and we simply have not noticed? How many signals have we received and dismissed as noise? How many artifacts exist in our own solar system and we have never looked for them? This is the hidden barrier, not distance, not technology, expectation. We are searching for extraterrestrial intelligence using assumptions about what intelligence looks like, what it builds, and how it communicates. But if alien civilizations operate on timescales longer than human, lifetimes if they use communication methods we have not invented, if they exist in forms we do not recognize as alive, we could be surrounded by evidence and never see it. In 2019, astronomers Abraham Loeb and Amir Siraj published a study proposing that instead of searching for radio signals, we should search for physical artifacts, probes, satellites, von Neumann machines, self-replicating robots sent by distant civilizations to explore the galaxy. These objects, they argued, would not degrade over millions of years the way radio signals do. They would persist. And if any advanced civilization had sent probes into our solar system in the past 5 billion years, some of them should still be here, orbiting in stable trajectories, waiting to be discovered. NASA has no program to search for them. No mission designed to detect artificial objects in deep space. We are listening for signals, but we are not looking for visitors. Why are we only searching in the ways we expect to find something? In 2020, astronomers using the Parkes Radio Telescope in Australia detected a signal at 982 megahertz coming from the direction of Proxima Centauri, the closest star to our solar system, just 4.24 light-years away. The signal was narrowband, a characteristic of artificial transmissions, and it appeared only when the telescope was pointed at Proxima Centauri, disappearing when the telescope moved away. It was labeled BLC-1, Breakthrough Listen Candidate 1, and for months it remained unexplained. Astronomer Sophia Sheikh led the analysis. She and her team conducted follow-up observations, scanning the star at multiple frequencies, checking for repetition, ruling out terrestrial interference. The signal did not repeat, but it also did not match any known natural source. For the first time in decades, astronomers had a candidate signal that survived the initial filters, a detection that could not be immediately dismissed. And then, in 2021, the team published their findings. BLC-1 was not from Proxima Centauri. It was from Earth. A frequency drift in the signal, caused by the relative motion between the source and the telescope, indicated that the transmitter was moving at a speed inconsistent with an object in orbit around Proxima Centauri. Further analysis revealed that the signal was likely from a malfunctioning electronic device on Earth, a piece of terrestrial interference that had mimicked the characteristics of an extraterrestrial transmission. The signal was explained, but the exercise demonstrated how difficult it is to confirm contact. Because even when we detect something unusual, even when it passes the first tests, even when it appears artificial, the most likely explanation is almost always human activity. We are drowning in our own noise. And this is the central problem of the Fermi Paradox. We are searching for extraterrestrial intelligence while simultaneously making the search harder by filling the electromagnetic spectrum with our own signals, our own satellites, our own interference. Every year, the number of objects in Earth's orbit increases. Every year, the radio spectrum becomes more crowded. And every year, the threshold for what counts as a confirmed extraterrestrial signal becomes higher. But in 2023, Astronomers using the James Webb Space Telescope detected something that no instrument had ever seen before. On an exoplanet called K218b, located 120 light-years from Earth in the constellation Leo, Webb's spectroscopic instruments identified the presence of dimethyl sulfide, a molecule that on Earth is only produced by living organisms, specifically marine phytoplankton. The detection was tentative, requiring further confirmation, but if verified, it would represent the first atmospheric biosignature ever detected on a world outside our solar system. Astronomer Niku Madhusudan at the University of Cambridge led the analysis. He cautioned that dimethyl sulfide could potentially be produced by non-biological processes under exotic conditions. But no such process had ever been observed. The molecule's presence suggested that K218b, a planet larger than Earth but smaller than Neptune, might host microbial life in its atmosphere or oceans, life that is chemically altering its environment in detectable ways. This was not contact, it was not intelligence, but it was evidence that life might be common, that the building blocks of biology, given the right conditions, inevitably lead to ecosystems complex enough to change the chemistry of entire worlds. And if microbial life is common, then the Fermi Paradox becomes even more disturbing, because it means the great filter is not behind us, it is ahead. Somewhere between single-celled organisms and galaxy-spanning civilizations, something stops the process. Something prevents intelligence from spreading. Something we have not encountered yet. In 1950, Enrico Fermi asked a question at a lunch table that has haunted astronomy for 74 years. He did not know he was articulating the most unsettling implication of cosmic statistics. He thought he was making a casual observation, but the question has never been answered. Because the more we learn about the universe, the more habitable it appears. The more exoplanets we find in the right temperature zones. The more organic molecules we detect in interstellar clouds, more evidence we gather that the conditions for life are not rare, but common, scattered across billions of star systems, waiting for chemistry to ignite into biology, and yet we are alone, or we appear to be. No confirmed signals, no megastructures, no probes, no artifacts, just silence. Which means one of several things must be true. Either life is far rarer than we think, requiring a convergence of factors so specific that Earth is one of the only places it has ever occurred. Or intelligence is rare, an evolutionary accident that almost never happens, even when life is abundant. Or intelligence is common, but it destroys itself, every single time, within a few centuries of discovering technology. Or the most unsettling possibility. Intelligence is common, civilizations are everywhere. They are silent because they have learned that broadcasting your presence is dangerous. The galaxy is not empty, but hostile. The civilizations which survive are the ones that hide. And once you consider that possibility, the great silence stops being a mystery and starts being a warning. Because if advanced civilizations exist and choose not to reveal themselves, it suggests they know something we do not. It suggests that making contact is not desirable. The visibility is a threat. And the fact that we have been transmitting radio signals into space for over a century, announcing our presence to anyone listening, might not be a sign of hope. It might be the mistake that every doomed civilization makes. Subscribe to Universe Uncovered because the universe is not empty. It's listening. And maybe we should be too.